So the next talk is from Lucas Stinchcombe, who is from Simon Fraser University.
Thanks. So this is joint work with my supervisor, Matt Amy. It's titled Polynomial-time classical simulation of Roetteler's shifted bent function algorithm, which is a little bit of a mouthful. So I'll call it the hidden shift algorithm, which is what it's called in the literature anyway. So some background, the hidden shift algorithm was originally devised as an oracle algorithm in order to give query complexity separations in the classical and quantum cases. Since then, it's been used as a benchmark for classical simulation where the oracle is given an implementation. So classical simulation is just, this is the room where everybody knows what that is, but quantum circuits and simulating that classically. So then, since then, it's due to some empirical evidence, it's been conjectured to be classically efficiently simulable or simulatable, whatever you want to say. And so in this talk, we'll actually show that this conjecture is actually true by giving a polynomial time simulation. So the way we'll do this is we'll take the circuit, we'll cast it to a sum over paths expression, which is like a formal expression that captures the action of the circuit. And then we'll give a rewrite system that's confluent for these expressions, and then use this rewrite system to give a straightforward simulation algorithm. So the setup is just to understand what the hidden shift algorithm is. We'll start with a vector space of functions from n booleans to the reals. We can see that there's like we can have potentially many bases, but we can single out two bases for this vector space, one being like a Dirac delta. So given an S here, it will output, the function will output 1 if and only if the input is exactly that bit string. And here we'll compute the parity given an S. We'll compute the parity on the bits that are indexed by that S. And so for any given function in the vector space, we might write it in this basis by just taking the points of that function. And over here, we would just do, this is a little bit more interesting. These are Fourier coefficients for the same function, and we can get those by a Fourier transform. And so a Boolean function in this space would be called, or a function in this space would be called Boolean if its image is in -1 and 1. And if it's, if f hat here, the Fourier coefficients are also a Boolean function up to a scaling by a constant, we'll call this a bent function. So multiplying by this constant square root of 2 to the n, we get the dual function, which is also a Boolean function. So we know what bent functions are. We might want to actually construct them. So the way we would do this is just get an arbitrary Boolean function on half the inputs and an arbitrary permutation on half the inputs, and just apply this construction called the Mariana-Macfarlane bent function construction, and this can be just checked to be a bent function with the dual that is closely related, and so we'll call these, the set of these functions, capital M. So now we're in a position to actually compute or actually define the problem of the hidden shift. So given a bit string S and a bent function in M, we'll call G the shifted function, which just computes F shifted by our bit string S. And then the hidden shift problem is just to compute S given an oracle which hides this S. And what does it mean to hide it? Well, we might have two different variations of an oracle. One which gives access to the original function F, its dual, and the shifted function, and this red oracle here that might give access to the original function and the shifted function. And so here we have query complexity separations in these cases, and interestingly in the red oracle case we have a time complexity difference that is just the result of we can do relative to this oracle, P does not equal BQP, because in the quantum case, we can extract this shift in polynomial time versus classically we need exponential time. So the red oracle is not actually that important for this talk, so we're going to talk about the blue oracle here. This has been used in simulation benchmarking with this circuit. where the oracles are actually implemented over this particular gate set. And it doesn't really matter the specifics about this gate set, but the important thing is that the number of controls here on the z's are fixed by some fixed m. So here, these oracles would compute the g, which is the shifted function in the dual, into the phase. And in previous works, without exception, m has been equal to 2. And the reason for this is because the CC-Z gate can be implemented with some fixed numbers of T gates. And so they wanted to control the number of T gates in their benchmark. And an important thing here is that this actually bounds the degree of these, the polynomials, the bent functions that are computed by at most m plus 1. So in the m equals 2 case, we have at most 3, degree 3 bent functions. And then Julian Codsey conjectured this to be polynomial-time simulable based on empirical evidence in 2022. So maybe we'll just talk about correctness here. So we'll just take the case where s is equal to 0 and pi is the identity. Well, we can just observe the action of the circuit on the 0 state. We get an expression like this. We know what f is because it's a bent function, so we'll just actually plug that in. And then some simplifications where we just notice that we have some constructive interference when two variables are equal and destructive interference when they're not equal, and we just resolve this to be the shift, which is just the 0 state. So what we just did kind of hints at maybe a possible way to formally express this. So we're going to define the sum over paths formal system. These look a lot like what I just did, but these are actually just formal expressions where S is a complex number, V is a set of indeterminates, and these P's and Q's are polynomials, Boolean polynomials. And yeah, Boolean polynomials just being polynomials over F2, where for every variable V squared is equal to V. And so we come to a proposition that we can actually, over our gate set, we can compute the sum over paths expressions in polynomial time, and the expressions themselves have polynomial size. And by polynomial meaning in the volume of the hidden shift circuit. And actually, we can read this as actually the size, the number of gates in the hidden shift circuit, because each qubit has at least one gate acting on it. And this is, again, just due to the fact that we have a bounded number of controls on our Z gates. So this will polynomially bound the size of our expressions, and then each tensor product or composition we use to construct our expression will also take polynomial size in the expression size. So some examples here. Let's take a Bell state circuit. You can kind of think of this as a contravariant functor of sorts where the orders are reversed. And let's just use our composition and tensor rules that come with the sum over paths expression or sum over paths formalism, and we get some expression like this. And so we can actually evaluate this expression if we wanted to by just summing over these variables over zeros and ones, and we would get a linear operator which is the same as the linear operator that we would have gotten if we just interpreted the circuit directly, so everything's sound and we're happy. And then another example, so two Hadamards, we'll just do the same thing. We do know that two Hadamards just has a circuit identity, which is just the identity itself. And so we need something the same, just like in the ZX calculus, where we would simplify this into the identity. So we need some kind of rewrite rule similar to how we have circuit identities. So for this, we'll introduce the HH rule, but not just, maybe some of you are familiar with the HH rule, but we'll allow something called the simple HH rule, which allows this simplification that we were just running into, but in the general expression of this rewrite rule will limit the number of variables that are being substituted to be at most one. So what this means is that here, if you look at this expression on the left, we get the expression on the right by multiplying by 2 and substituting z and for y. And this is a valid application of the simple HH rule because z is just one variable. But we won't allow things like substituting z plus w into y. So, and just to fix vocabulary, we'll just call this an application of the simple HH rule with respect to x, where x is the variable that we're kind of factoring out of the expression. And importantly here, we've reduced the number of variables by 2. So here we have 3, now we have 1, and it's more simple than before. So we'll come back to the hidden shift circuit. We had our circuit, which is used for benchmarking, and we'll, in polynomial time, construct the corresponding sum over paths expression. And it has this kind of hideous shape, and it looks not great, but one simplification we can do is that we had this pi parameter in the, which is a permutation in the construction of the bent function. So we can actually just ignore this by relabeling variables through like an isomorphism of rings, if you want, if you will. And I'm kind of sweeping stuff under the rug here, but basically we can just move stuff to the state, and there's no rule that cares about the order of the variables in the state, so we can take pi equal to the identity. And so at this point, great, we have this sum over paths expression, like what can we do with this thing? Well, naively, we could just take our rewrite rule, of which we only have one, and just apply rewrites until we can't, and then finally evaluate this sum over paths expression by just summing over the variables. So this gives us kind of two problems. One is that the evaluation has cost exponential in the number of variables, because we're summing over 2 values for each. And the other one is, okay, how do we choose a rewrite to apply? So we want to simplify this before we get to a point where we would be able to evaluate it, but we don't know what order we would apply these rules in to get what we want. So number one is actually solved because I briefly went over the proof of confluence. Well, that proof was actually just a sequence of simple HH rewrites, which means that there is a rewrite sequence that gets us down to the final state that we're interested in. And the final state, if you notice here, has no variables, so the evaluation is trivial. And so number two, we can invoke a little bit of wishful thinking and hope that every sequence of rewrites actually completely simplifies our expression down to the final state, which is the result of the hidden shift circuit. So this is actually the property of confluence. And so we'll just say here that A rewrites to B confluently if for all C and D such that A rewrites to C and A rewrites to D, we have that C rewrites to B and D rewrites to B, which is just to say that whatever you've done in the past, there's always a way to get back down to the final state. And so you can just forget about what you've done before. So here's an example to sort of see what sort of degrees of freedom we have in choosing a rewrite. So let's say that we want to apply a simple HH rewrite with respect to x. Oops, sorry. With respect to x. So what we might do is rewrite, so apply a substitution where we substitute w in for y, or we could potentially substitute y in for w. And the question is, well, does this matter? And intuitively, it would seem like not. And intuitively, you would be correct that, yeah, if substituting z in for y rewrites to s confluently, then substituting y in for z also rewrites to s confluently, and vice versa. So with that, I think that will basically be enough to just get what we want here. So we can do now just a case analysis, basically, where we've noticed that in our expression we had this variable set. We can easily just show that all rewrites will be with respect to the first 4 variables for each I. And just to give an example of how this proof works, let's say that we considered only rules with respect to xi and zi for some I. Let's look at the potential rewrites that occur as a consequence of this. So we'll take these relationships here, which are the basis for the substitution. So we're going to juxtapose these here, and we'll notice that, okay, this ZI rule cannot be executed because it has too many variables, and so we have no choice but to execute the XI rule. So YI gets WI plus the shift, and after this, we track what happens to the other rule that we had, which is the ZI rule. And so here we'll notice that actually what happens is this linear sum gets added into the lower linear sum here. And so now at this point we just have one variable and we can just do the corresponding rule for ZI. And we've annihilated both rules. So what this simple little simplified example tells us is that we have a dependency between rules. So we have a dependency of ZI on XI, and in the similar way we can just expand this to the rest of the rules that we had. So we can see we can just do the same thing. There's a little bit more complication with respect to the other rules, which are, I don't want to confuse anybody, these are just the same simple HH rules but taken with respect to different variables. It's a little bit more complicated here just because we have potentially nonlinear terms, but we can just do the same sort of strategy and find that there are dependencies between these rules that we have to execute, and we come to a claim here that, okay, so every valid rewrite sequence has to satisfy the dependencies that we've constructed, and every rewrite sequence which does will terminate with the final state S, which is the result of the quantum algorithm. So then, at this point, basically the two problems that we raised, the number of variables and the choice of rewrites, is solved. So we can just write an algorithm which does exactly what we want, which is just to take our hidden shift circuit, turn it into a sum over paths expression in polynomial time, and apply these simple HH rewrites until we cannot anymore, at which point there are no variables, the evaluation is trivial, and we just return the result, which is the exact shift. And so the theorem is, algorithm 1 simulates a hidden shift circuit over gate set G and polynomial time. And this is generic in the sense that there's nothing that cares, there's no analysis of an algorithm that happens here, and in principle this can be done with any circuit just without a guarantee of efficiency. And so we have open questions whether this method works for other sum over paths expressions. In particular, we had here a quantum deterministic algorithm, so whether it's effective for non-deterministic algorithms. At the end, we would have to do some sort of sampling, but whether it can be augmented to handle these cases. And then the other question is, okay, instead of having a simple HH rule, what if we allowed linear or affine substitutions in our HH rule? How does that affect the property of confluence? And that's it. Thank you very much.
Okay, thanks, Lucas. Do we have any questions?
Thanks for the nice talk. Is the HH rule, so you're just applying the HH rule, right?
Just the HH rule, yeah.
And that's always terminating, is that right?
Yeah.
Because you remove a variable.
Because we're always removing variables. Yeah.
Okay.
So it's noetherian if you care about these terms, but.
So that theorem you had that said all of my terminating, if my path terminates, it terminates with S.
Yeah.
It's actually that all paths terminate.
All paths do terminate, but all paths terminate with S is the main part of the.
I see.
Yeah.
And okay, no, I've forgotten the second thing. I'll ask you at lunch.
Okay.
But
No
anyway,
problem.
thanks.
Cool. Thanks.
So I know you put this in your open questions, but do you know any example of a larger class of expressions that is similarly efficient to reduce?
That's a good question, and that's something that we should be doing. But there's like obvious stuff, like I guess the Bernstein-Vazirani algorithm, but those are easier. So we haven't really looked at other examples. The question that we're really asking is whether these rewrites are confluent in general. So if we can write it in this sort of flavor of some of this flavor of sum over paths, we're trying to figure out whether we have confluence in general, not just for these expressions. Yeah. So,
Last question? No. Okay. Thanks very much.
thank you.